Hello class. Okay, so this is a tutorial for homework 12.1. This is about ANOVA, Way ANOVA to be precise. And before we dive in, I'd like to be able to go over a little bit about how kind of in the nuts and bolts of it, not to get too technical, are about how Way ANOVA is different than that of the t-test. Okay, so you kind of know this a little bit already. You use this a little bit in your previous homeworks. But so if we go into calculators here, and this is just for kind of tutorial purposes, just to kind of establish a background. We've done a little bit with the normal distribution here, right? So it's this kind of normal bell curve that we're kind of well familiar with, and we can change the mean and the standard deviation to be able to kind of change what the values on the x-axis look like, right? So this is kind of what we're so far most familiar with. In t-test, we use the t-distribution here. Now you see here it looks a little bit more narrow, but as we change the degrees of freedom, right? So the degrees of freedom is essentially the total number of samples minus 1. We get more or less a thinner, or if I go out to 100, wider distribution, and it kind of converges to a certain shape. As you see, 100 is no different than really 1,000 to look a lot like that z distribution that we had before. So it basically will converge to look very similar to a normal distribution if the t-distribution has enough participants, or enough n in it, so enough samples are being drawn into the test. But the t-distribution will change dependent upon whether or not you have more or less people in your analysis. Now, if we go into stat calculators and look at F distribution, and this is the one that ANOVA uses to be able to determine if in fact a test is statistically significant or not. You see it has two different degrees of freedom with the numerator and the denominator. That's degrees of freedom, numerator degrees of freedom, and denominator degrees of freedom is the denominator, or den degrees of freedom. And what this represents is really number of groups and then the total n as well. So because a one-way analysis of ANOVA really looks at comparisons between 3 or more groups, right? So a t-test is appropriate for 2 groups only, comparison between 2 groups, and an f-test can go anywhere between 3 to as many groups as you want to do it. There's really no limit, although there's a practical limit probably. So as we change both of these things now, it's going to change the way that this distribution is going to look. So you see it has a little bit of a skew here where it's kind of leaning to the left. If I change this to 1, wow, it looks really different here, right? And so this the area under the curve that we're looking at here really looks much different than what we were looking at here, and that's because as we change the degrees of freedom, it goes into this function that essentially is going to change the shape of the distribution. So the distribution could look something very funky like this, or if we increase this by a lot, it can look something a little bit more normal. This is still kind of out there, something a little bit more skewed. And so you kind of have to be able to understand when you're calculating this, when you're kind of performing this test, that there are things that go into it that's going to change the overall, not just the width of the distribution like in the t-test, but the overall shape of it as well. Okay, so that's how it's a little different, it's a little funky. Don't let that throw you off. You don't have to really worry about this. There are no questions that require you to use the F calculator, but it's just to give you kind of a baseline understanding. Okay, let's jump into the actual homework now. All right, so here we are, and this is question 3 of kind of a preview of the homework. I've already kind of filled out the null and alternative hypothesis. So the null hypothesis is always going to be, within this section, there's 3 groups, and that the means of all 3 of those groups are going to equal one another. The alternative hypothesis is that at least one of the means is different from the others. Okay, so in this question, they just give you the readout of the ANOVA table here. So this is an ANOVA table, so it has SS, which is sum of squares between groups, within groups, and the total. So you add up these two, you get this. Here's the degrees of freedom. So here you have really the numerator and the denominator. Okay, this is like what we were looking at before. And then we have this is basically the mean sum of squares. So essentially this is this number divided by this number. Okay, and this goes over here. And then you have your F statistic. Okay, this is just like the T statistic, but this is for the ANOVA. And you get this number by dividing this number into this number. So we have 1.66. Here's a p-value. You should be pretty familiar with that. Is F critical is the statistic you need to kind of surpass in order to be able to get a significant test. So let's see if we can kind of do this by looking at the F thing here. So we know what the numerator is, which is 2. Okay, and we know that the denominator is 119. All right, so it's 3 groups, and there's a total of 122 children. Compute. Okay, so we're getting pretty close to that. So again, if our significance level is 0.05, all right, we have kind of a weird thing going on here. We're going to change it to the other side. I'm going to switch this to what our significance level would be, 5, compute. And so hopefully what you're seeing here, and that you can compare pretty readily, and that we do not have what looks like our normal distribution, but this is the distribution for this particular test given the number of groups and the number of participants in that group. And what we found is that if our significance level is 0.05, that means that, so we're looking at a probability of 0.05, then our critical F statistic, to be able to kind of have make sure that our outcome is greater than chance, or a 95% chance, our critical value has to be 3.072, and that's what we have here. Okay, they rounded a little bit, but they have 3.072, and so this kind of gives you a reference for exactly what you need to have. Now take into account too, I didn't actually dive into this too much, the F statistic, as you can see, is a difference between that and the T statistic, or the T calculator. So the T calculator will go negative. And here, when you're looking at the F calculator, it stops at 0. It does not go negative. So that's also something that makes it pretty distinct from that of the from the T statistic, okay? And that's going to be different than if, okay, I'm going to exit out of the T calculator. I'm going to go back to the normal calculator. Here, obviously, my Z statistic here, a normal calculator, Z calculator, it's kind of the same thing, can change depending on if I change the value of what my mean is, and so this is going to be very variable, but of course the tails are never going to touch, so essentially they both go on forever, whereas the F distribution, it will go all the way up forever, but it will not go past 0 on the x-axis, but it will go up forever on the y-axis, okay? Hope that wasn't too confusing, but essentially you can kind of now draw a comparison between what this table is talking about here and how it actually looks in terms of area under the curve, okay? So that's a little something to kind of show you the kind of uniqueness of this test compared to other tests. So back to the homework. So what is the test statistic? It is, okay, around two decimal places. This is the test statistic. 1.66 is what I'm going to put. Okay, check answer. Nice work. Thing on was the p-value, around to 3 decimal points, 0.195. Check answer. Well done. That part. Hopefully you'll be able to fill onto your own. I'm now going to jump to another question. That is hopefully, yep, this one's going to use data. Okay. And this will be hopefully a little bit more informative about how you actually now use data and how this test actually does some of its calculation in a more practical way. Okay, so here we're going to go to Stat ANOVA one way. Okay, I'm going to highlight all of them. I'm holding down Control. I'm going to click them all. There doesn't seem to be asking me if I need to do this. I'm going to select it anyway. And I'm also going to select this just because it's going to give me a little bit more information that I'm going to convey to you that might kind of help you in the future. Alright, null hypothesis. They're all going to be equal. This, at least one, is going to be different. Great. Alright, that's pretty much going to be the same for all of them. So that's going to be pretty easy. So I'm back here. I put my data in. I've highlighted these, but this is just to kind of be able to go more in depth. You're not going to need it for this question. I'm going to click Compute. Okay, it gives me the mean and then the standard deviation and the standard error for all of the 3 columns that I have. I think this is about growing trees or something, either with no treatment, fertilizer, irrigation, or fertilizer and irrigation. Here's my ANOVA table. My F statistic is 2.37, round to 4 decimal places. Okay, I think it's just 2.372.3706. Hopefully I did that right. Okay. Find the p-value, round to 4 decimal places. I only have 4, so I'm going to go 0.1088. Okay, thank you. Okay. Alright, so this is something, again, you're going to be a little familiar with. This is a concept, and I'll let you kind of tackle it from there. Now, what I want to kind of be able to show you as far as like when I selected this Tukey HSD, it's going to basically tell us now if the any of these things actually differ between one another. Alright, and so what we're looking at here between all of these different comparisons is we have the no treatment subtracted from fertilizer, irrigation, fertilizer, and irrigation. So it's doing basically side-by-side comparison between all of the groups that we have here and telling us if these direct comparisons between one group and another group are statistically significant. We can see that they are not. Now we're going to do fertilizer subtracted from irrigation, fertilizer and irrigation. Nope. And fertilizer and irrigation subtracted from, or irrigation subtracted from fertilizer and irrigation. This one comes pretty close. So we can kind of make somewhat of an inference that fertilizer and irrigation seems to have a positive difference on whatever outcome variable is compared to irrigation. Alright, we can look at that by looking at, this is called the dot plot. Alright, so we have so many samples here. If I bring up the data again, it's basically just plotting the data here with the groups on the y-axis and the outcome variable on the x-axis. And this line here is the grand mean. So this is the mean of all of these together. Alright, and so if essentially if we had a statistical difference, then we'd be able to say that one of these groups is different than that of the grand mean. And then when we do the Tukey HSD, we're able to look at which group is actually different from the other group for the most part. And so what we see is we kind of saw before was that irrigation and fertilizer seem to be different from one another, or they're the closest. And here we see that fertilizer and irrigation, that irrigation is pretty low and fertilizer and irrigation is pretty high. Potentially, if we collected more data, we would be able to get a little bit better idea of whether or not that's true. Just for fun, let's go ahead and go into calculators, F statistic. We know that there are 4 groups, but we're going to do 3 degrees of freedom because it's 4 minus that 1. And then we're going to do, we have 20 here. It's going to be, I think it's going to be 20 degrees of freedom minus K, and K I think is the number of groups, so that's going to be 16. And we're going to compute that here. As you can see here, now I'm curious about what my F distribution is going to look, or what the area, my critical value is going to be, 3.23. And if we go back to what our results were previously, what was our F value? Was 2.37, 0.1 1. So if I actually put in 2.37, compute, you see, oh wow, that worked out amazingly well. I'm actually surprised. Not at this, but at myself. And you see, so I did 2.37, that gives me a p-value of 0.1088, and that's what I have here. So this is the distribution it's drawing from, given a numerator of 3 and a denominator of 16. So the numerator is the number of groups minus 1, and the denominator is the total number of samples minus the number of groups. And that's how it figures out this distribution. And so our critical F value would be, if I, again, were changing this to 0.05, I added another decimal again, would be 3.24. Okay, and so I would either need to increase the overall number that I have here. So if I were to add one more person to each one, and then I'd have to continue to change this. You know, my critical F value continues to go down. If I were trying to get to an F value, F statistic that was similar to that of what I had here, I kind of have to like either do a power analysis or something like that, which is not outside the scope of this, but essentially I have to continue to increase the number of people I have in each group, or trees in this case, in each group, in order to continue to drive my critical F down so that it drives me closer and closer to being able to get a p-value that is less than my significance level of 0.05. Okay, so it's very long-winded. I hope it was clear, and I hope that was helpful. If you have any further questions, please feel free to reach out, and thanks for watching.